Well, our next speaker, like our first speaker, is really somebody who really needs no introduction. Rob Socolow has been one of the greats of sort of the energy world for many decades. He is Professor Emeritus and Senior Research Scientist at Princeton in the Department of Mechanical and Aerospace Engineering. He is head of the Carbon Mitigation Initiative at Princeton, which has had a remarkable run to date. I think it's been going for about 14 years, which is a remarkably long time to have one funder interested in the research of one group. He serves on the advisory board of Lawrence Berkeley National Lab. He serves on the editorial board of Energy and Environmental Science. He serves on Deutsche Bank's Climate Change Advisory Board and has far too many awards to list. So I'll just pick one, which is the 2003 American Physical Society Leo Szilard Award for Leadership in Establishing Energy and Environmental Problems as Legitimate Research Fields for Physicists, and demonstrating that these problems can be addressed with the highest scientific standards. He's also a fellow of AAAS in the American Physical Society, and so I'm pleased to turn the podium over to Rob Socolow.
Three wonderful talks. I've learned so much, and thank you very much for this invitation, and thank you very much for having a Rutgers Energy Institute and for the vigor of its program. The first talks have all been US based, and I got the organizers to agree that I could take a global focus because the climate problem, which specifically interests me and many of you, is global, planetary. So I thought just for a moment to connect the two, when the US has or hasn't got a climate policy, a carbon price, vigorous R&D and so forth, why does it matter globally? Well, first of all, we really actually contribute substantially to climate, to the emissions on the globe, about 20%. Second to China in quantity now. So anything we do directly will have an effect on a global problem, but it's not the whole story. When we develop, say, PV or some kind of battery technology, it's available to everybody. And so the vigor of our own industry produces options for others, particularly lower costs, because we have reduced technological uncertainty and shown how to do something. And then the third is a more moral or persuasive argument that others will follow us. We actually are leaders in many domains. We're thought of awfully well in the world, maybe much better than we deserve to be. So I'm going to give you a quiz. I want you to locate yourselves in one of these four boxes. Make a choice. Take enough time to do that, where you have to answer two yes/no questions. Are fossil fuels hard to displace, and is climate change an urgent matter? I'm going to ask you to vote. So I need another second or two, but okay. So how many of you put yourself in the top right quadrant? 1, 2, 3, 4, 5. Okay. And how many of you put yourselves in the bottom left quadrant? About 3 times as many, maybe 15. And how many of you put yourselves in the bottom right? Most of you. That's interesting. And if you're in the top right, much of the fossil energy industry is there. You can go to sleep at night pretty comfortably because you're producing your industry is producing a gas that is going into the atmosphere. But all in all, maybe it's not a hoax that I think Rush was due to Senator Inhofe, if I have the right senator you had quoted from. But it's just something that's exaggerated. So you're comfortable. And if you're in the bottom left, you're also comfortable. Because either nuclear will sweep fossil away. That used to be, that when I was a youngster in this game, that was commonly held truth, that coal would be displaced by nuclear across the board, and certainly well before now. And if you're a renewables guy or gal, likewise. It's just a matter of getting on with the job. And she also sleep well. Those of us, the majority of this room, maybe 80% of you, don't sleep well at night, as I don't, because those two yes answers introduce a problem. I decided to put temperatures on these three quadrants. If the people in the bottom left or right are correct, then we might be able to meet a targets that the international community is talking about. We put on some policies and renewables and win the game. Renewables efficiency and perhaps nuclear win the game. If the people on the top right are correct, we don't have any carbon policy to speak of, business as usual prevails, and this number means that average temperature rise, the temperature on the planet average over the surface, say in 2100, relative to the temperature in, say, 1800. So it would be about 5 degrees Celsius hotter. And my own sense is that we would be doing a very good job if we could get to 3 degrees, given the world we actually live in, and that the real conflict that we should be discussing is between 3 and 5, because I think 2, and that part of my talk will be, this is the world target today, may entail risks on the solution side greater than we want to experience. So I think I was about 10 years old, and I think many of you were 10 years old when you got caught up in this particular paradox. What happens when an irresistible force meets an immovable object? Do you remember learning that in probably pre-high school? Am I right? It kind of was fun. Well, I think this is about where we are. If you're in the bottom right quadrant, this is just another way to say it. The irresistible force is that fossil fuels are as vital as ever. I'll show you a graph of that in a moment. The immovable object is climate change, which looms ominously, is not going to go away. And we really don't know how this is going to get resolved. At some unknown pace, but conceivably soon, the world will become seriously engaged with climate change. It's less engaged than it was 5 years ago, as Rush was telling us. Some kind of a pendulum is at work here. At least I don't know whether in 2020 we will be looking at this graph and showing the same graph, or whether we will agree that we've turned a corner and we're moving forward. We are dealing with a lot of political uncertainty at this point. Just to remind you of this statement that the fossil energy system is the irresistible force. This is a graph of where coal, oil, and gas are gray, red, and gray, green, and red, respectively. And they're most of that curve, and the renewables, hydro is split out, the nuclear, and then the other renewables are in there, and they're adding up to something between 10 and 15% of the total. This is global, and this is primary energy, basically. There's some conventions in there, but you look at that graph and say, not much has happened in the period of time that Rush and Paul and I and many others have been working pretty hard to try to make something happen. We haven't bent the curve. Many of others of you, excuse me for naming only 3. I'll show you one graph on impact, which I think is particularly fun. It's from Jim McCarthy at Harvard, and since he's at Harvard, he's starting with Massachusetts, and he's imagining Massachusetts moving southward in the sense that the summer climate will be the climate of X at date Y, depending on assumption Z. Okay, the two assumptions are that we take carbon seriously and that we don't. Higher emissions and lower emissions scenarios. Already, Massachusetts is around Connecticut or New York. And depending on the two graphs, let's see, I do have a pointer here. Let me see if I can do this. Is this what do I press? Try that. Yep. And then we have the two choices here for the second date, here and here for the third date, this pair. So if we don't do any climate policy, we will see South Carolina and Massachusetts. New Jersey will be obviously somewhere in central Florida, and not much fun. And that's up to us. Now there's a second graph where you can say, what about the uncertainty of the models? And the models are about as uncertain as that, so you'd multiply something approximately equally uncertain, and you might get yourself down into Cuba if you've got bad luck in both. So the most recent formulation of the climate change problem by the IPCC in its publication end of September last year presented the world with a fourth way of thinking about about targets, fourth vocabulary for targets, called cumulative emission targets. We started with emission rate at some future date. Actually, the Wedges paper that Steve Socolow and I wrote was that the emissions in 2050 should be no larger than today. Concentrations never to be exceeded, 450 parts per million or 550. Surface temperature never to be exceeded, that's the 2-degree game. The new person in town is the cumulative emissions from now on, a carbon budget. There are all kinds of ambiguities, but that's out there, with a coefficient that roughly 1 degree Celsius is 2,000 billion tons of CO2, and or 500 billion tons of carbon. So we have the question, how much carbon are we going to emit altogether? And I think we're once and for all past the peak oil wishful thinking, which somehow depletion would solve the carbon problem for us. There's so much buried hydrocarbon, people are very clever about getting it out of the ground. It really does appear that we can raise the atmospheric concentration hugely if we pay no attention to trying to keep it from rising. As soon as we raise the issue of budget, we are in some very interesting territory that we haven't talked about in a serious discussion among the policy wonks and the general public and the congressmen. It was initially presented in the IPCC report as all about 2 degrees, and I think that's a disservice because the concept is much broader than that. And if you had 3 degrees as a target, you'd be raising the very same questions. When to take the carbon out? Because it doesn't matter when you take it out on this budget idea. I've had this in my head for a long time because it's not a bad model of the carbon in the planet is that half of what you burn stays in the atmosphere forever. Obviously, in the simplification, some of it goes away earlier and some of it goes away very long time, but if you say half stays in, then you realize it doesn't matter when you put it up, or where you put it up, or which fuel you burned, or what you used it for. So all of those issues are out there. And we actually have ahead of us, one way or another, this conversation, which is international, intergenerational, and interfuel. So we can talk about that some more, but of course there's one escape hatch. Which is if you burn a fossil fuel, but you capture the CO2 and put it below ground, then you get a freebie. And so we may have a lot of that in our future, which would allow us to use more of the fossil energy below ground. So this is the framing that is going to persist, and it was really presented, in my view, not as forcefully as it should have been in the Working Group 1 report, and then Working Group 3, as far as I know, didn't do much with it at all, but it's there for the plucking. So let's move to technology and a Rorschach test. This is a picture of the US highway system. What do you see? How about a few comments from the audience? What do you see? Who sees something?
Circulatory system.
You see a circulatory system, like a veins and arteries, okay? What else do you see?
Neural system.
Huh?
Neural system.
A neural system, okay.
Variable density.
Variable density, most of it on the East Coast, mirroring population. You see a political achievement. This was a 50-year commitment in the Eisenhower period that actually got done, and one looks at that, and I want to show that to everybody in Washington and say, you know, we did things like that. We also did rural electrification and a grid. Do we have that kind of will? This is what we did. I also think we see congestion. We see trucks beating rail. We see suburbia. We see oil, and we see carbon, and probably a few of you have some other things. They're all in that picture. The 50-year growth of US emissions is in this picture, and in this one. Almost the same 50 years. Much less familiar a picture, but these are the power plants of the US by size, type, and location. You see an interesting go game going on here where the Appalachia manages, yellow is nuclear, and the red has excluded the nuclear from the Appalachians. So we have efficiency to deal with as one of the ways in which we can react to all of this. Very important. lots of things to think through, some of them captured in this picture: public transport, technology for lighting, which is an incredible success story. Ditto the variable speed drive motor in industry. Cogeneration is at the back right, at the bottom right. And in the middle, some question about lifestyle. How much can we, in fact, displace travel, business and personal travel, with IT, information technology? We're already doing some of that, not going to the bookstore, but buying on Amazon and various other things that we do. Telecommuting. A very interesting area that will affect demand, that forces you to think across categories. I've found that when I give a talk on this subject and I don't mention population, there will be a person standing up at the end of the meeting saying, "Why didn't you mention it?" before he or she finishes the sentence, usually she. I have to say, you're about to ask me about population, so I have looked for one slide that would sum up some of the interesting questions about population. The United Nations kind of corners the market on population projections. Hardly anybody else does authoritative population projection. And it has 3 scenarios for 2100. The middle one has 2.1 kids per mom. All the countries of the world somewhere around mid-century, and therefore the population flattens out because that's replacement level, and it leads to 10 billion people. If you add an extra half kid per mom around that time, because of the tyranny of exponential growth, you end up with 16 billion people. And if you have one drop by one to 1.6 kids per mom, you get to 6 billion people. There's a 10 billion person swing in 2100, depending on a half a kid up or down from replacement level. That's a pretty interesting result. And there are some of you in this room who are contemplating family size. And I just would like to say there is probably no resource decision you are going to make as impactful as the decision of how many children to have. It is not just about those very fast reproducing populations in the developing world, most of which are not so fast reproducing anymore. And if you take that 6.2 billion people and extrapolate at that same rate another century, you're down to about between 2 and 3 billion people, which we didn't have as a population all that far back. But this is a very happy view, I think, of how we come to terms with environmental limits, with a small amount of social modification and not war or plague to get to the same place. So the population has to be rebundled with this rest of this conversation. When I was involved in this subject in the 1970s, environment and population were twinned at the hip. John Holdren, Paul Ehrlich, and Ann Ehrlich's book, which was the best textbook of the day, was called Ecoscience: Population, Resources, Environment. And then it got fissioned. Population was hived off by the environmental community. I want to bring it back at least in one slide. If you work out the emissions per capita for the world, we have about, for carbon dioxide only, we have about 35 billion tons of carbon emissions and 7 billion people, which works out to 5 tons of CO2 per person per year. And the US emissions rate is about 4 times that. And China and Europe are well above 5 now, more like 8, and much of the developing world is 1 and 2. So what about understanding our own emissions? Well, here are 4 ways to use up your quota as an average global human. If you drive 20,000 miles, 18,000 miles a year, and you get 45 miles a gallon with your car, or 9,000 miles with a 22 mile a gallon car, you will use up your quota for the world, and many of you do. If you fly, the coefficient is roughly, it's like a 45 mile a gallon car today to be in coach class in commercial aviation with mostly full planes in the US. If you start going business class, you end up having a larger amount because this is taking the total number of seats to allocate the energy. Or flying private planes, obviously, is worse. Home heating in New Jersey, my own home, it's about that quota. Natural gas, which should be very easy to figure out, but our electric bill comes in therms, and what's a therm, and then you have to work it all out. But if you do, you'll figure out that you're using about 5 tons. I recommend that as a homework problem for some undergraduate courses, to go get the kids, go back and get their parents' bills and work it out. Lighting, of course, is the more, or any other electric use, is more complicated by the question of how carbon intensive is your power. And there's a large ratio between the carbon intensity of Ohio and the carbon intensity of Oregon and Washington. But New Jersey's sort of in the middle, about half as intense as coal. And so you can produce 800 kilowatt hours a month. And you're used up your quota. So any one of these, for many of us, uses up our quota. Some of us have to admit that flying beats the rest of it. And so you get a sense that it isn't all that easy to get our carbon emissions down. And one of my messages here is we've got to look at this problem from both sides. I call two sides of a mountain. The climate scientists are climbing up one side and looking at how, gradually understanding more and more what we're doing to the planet. Another set of people are on the other side of the mountain trying to figure out what we do about it, and we're not enough in communication. I learned that the Rutgers has an energy institute and a climate institute. Those are two sides of the mountain. They should join. The university is another place where you can calculate your share. And at Princeton a few years ago, just by working there, I have a 9-ton per CO2 per year obligation. That's for heating and cooling the buildings, running the power systems for fume hoods and lights and computers and whatnot. Doesn't include commuting. I'm told that there is no equivalent Rutgers accounting at the university level, but the Princeton, at the Board of Trustees level, when this was the flavor of the month, New Jersey was making a target. Kyoto was about, various European policies were about targets. U.S. Waxman-Markey was about targets. Princeton created a target of 1990 emissions in 2020, even though they were going to build a lot of more real estate, and it's operating. The people who run plant engineering are trying to get to meet that goal, and it's a very strenuous goal. I think the people in this room should hold the Rutgers trustees responsible for doing the same exercise and be more conscious of it. Without that, there's no unifying pressure. I'm not sure Princeton will make it, but it's still operating. The students are no longer interested. It's not the flavor of this month, as many of you know. Divestment is taking the same energies. Let's go back to the power plants themselves. That was a little unit on demand. This is a graph, I've just gotten an updated version, which is a fascinating graph of when our power plants were built that are running today. So it goes all the way back to 1940 at the bottom left. It goes out to 2011 on the bottom right. And colored black for coal, red for nuclear, blue for natural gas, and gray and yellow are the others. Gray is the renewables. Gray is the renewables, which shows up. It's an interesting story because there's this famous peaking of overbuilding of natural gas plants over here, which has more or less stopped. But this didn't drop all the way to zero again because here's the renewables energies of the last 5 years coming in to keep it quite a high level altogether. This is capacity in gigawatts, and many of you know that when you take the renewables nameplate capacity, you're going to produce about 1/3 as much kilowatt hours from that same kilowatt of capacity as when you have a gas or a coal plant, particularly a coal plant, because it's not going to run much of the time. It's about 20–30% load factor. But it's a very interesting graph, and what I particularly want to show you is the middle of the graph over there, because this is 30 and 40 years ago. 1973 is right at the top of that peak. Coal plants mostly built around that, on average around then, nuclear maybe a decade later, all of them getting old. We were talking about the aging workforce of the utility industry. There's a corresponding workforce of the facilities themselves. So we are confronting in this country, and it's a sleeper issue, it hasn't surfaced enough, that both coal and nuclear are getting old. Everybody knows that in the industries because the most important political victory they want to win is to be left alone to keep running without any pressure to shut down. Both the nuclear and the coal people see the problem exactly the same way. They paid for the capital. And there's some end to this game. For the nuclear people, it's a matter of relicensing a nuclear plant from 40 years to 60. If you look at the graph, you can see that that has to be underway already. It is. Almost all the plants are being renewed. Will they go from 60 to 80? As far as I can tell, no. Same questions are arising now in France. They may not even go to 60 because there are a lot of running costs as things get old. Creaky people, creaky plants. And for the coal industry, they've been trying to shut down the environmentalists have been trying to shut down some of the dirtiest of the older coal plants for a long time. It's a very familiar argument, and it's now an objective of EPA to try to do this. But we're confronting, in other words, we've had low-cost power in part because we've been running on old stuff, and we got to build something back. Maybe not one for one, because efficiency has some role in all of this. But if it's 2 for 3, we've still got to find stuff. And we haven't really confronted how much new construction there is, even if there's no load growth whatsoever. So we have options like building a coal plant with capture and storage. This is a figure that was developed by a community of people working in capture and storage for me, and I wrote an article in 2005 in Scientific American called "Can We Bury Global Warming?" And that's the picture that's particularly the core of the whole article, because we tried to work out quantitatively what kind of volume below ground would be required for carbon dioxide associated with a coal plant of a given size after it ran for a particular length of time. And those yellow lily pads in that picture are the CO2 formations, and it's a very generous assumption that's embedded in that. It's probably a lot larger areas. We're talking about a monumental enterprise to put the CO2 below ground, but one of the ones we may really do. There's carbon dioxide capture and storage practices going on. This is a particular facility in the middle of Algerian desert where natural gas comes out of the ground with too much carbon dioxide in it to be put in the grid. Carbon dioxide is removed and injected into a formation in the desert where it stays. And that's an expensive project. They're actually no longer capturing the CO2. They're no longer injecting the CO2, they're venting it after they separate it because there's no social pressure to do anything else. But they did for about 5 years do that. Nuclear is another option. One of the reasons I'm so determined to force people to think about climate change in terms of both the problem and the solutions is because nuclear power looms so large on this discussion. It is low carbon and it is base load, so it runs nearly all the time. And there are lots of people, including increasing numbers of environmentalists, who say, bring it on, we've got to do something. And I don't think we can bring it on yet. This is Fukushima before its accident. And I just want to show you one piece of science about why that accident happened. You can't shut a nuclear power plant off when you stop the nuclear fission. There are so many radioisotopes have been formed during those fissions that they produce heat. And what this graph is the percentage of total power which is still being generated by those radioactive isotopes as a function of the time after they shut down. And I picked out there one day, it's a log scale on the horizontal axis, one day, 1% of the total emissions. So a 1,000 megawatt electric power plant is 3,000 megawatts thermal, 30 megawatts of heat are being generated at one day, which boils a lot of water. So if you don't continue to cool a plant because somehow the cooling system has failed, everything around will melt, gases will be released, and that's exactly what happened at Fukushima. It was supposed to never happen. Backup systems were supposed to work so that if a power plant had some problem and had to shut down, the water would continue to flow over the fuel rods. It didn't happen. It didn't happen to 3 Mile Island either. And it's not a pretty picture. But the number one issue for me about nuclear power that is the coupling with nuclear weapons. So if people who were arguing that we should add nuclear power to the mix of low carbon technologies would say in the same sentence, in the same breath, and that means changing the world order around nuclear power and nuclear weapons, making it very much more international and globally governed. And we have to figure out how to do that, and if we can't, we don't go forward, but maybe we can. I would feel very differently, but people wish this problem away. The genie's already out of the bottle. We can't do much about it, arguments like that. It's a political problem, it's not a technical problem. Well, baloney. We have to have a way of feeling comfortable with the whole world getting the same technology. Another one of the dodges is, well, only the countries that we're not worried about will develop this technology. Well, who's we who are not worried about it? If a technology gets developed by some countries and it brings with it prestige, every country wants it. And the Bush administration, the W. Bush administration, had the idea that we could have sellers and users, I think was the phrase, and providers and users. And the users would include countries which were not allowed to have any access to the technology. They simply let it sit there. That's completely misguided. So widespread deployment of nuclear power lowers global CO2 emissions, but it increases the risks of nuclear war. Now, my generation, 50 years ago, when we were the age of the students in this room, really learned from our elders that our #1 job was to keep the world from nuclear war during our lifetimes. And we've sort of done it, but we haven't made it unthinkable for the next 50 years. And so it remains right up front as an assignment for the next 50 years. And if it is not a good exchange to deal with climate change and bring on nuclear war because there's insufficient controls, insufficient taboos of the kind that we have at this time. The Iran story is a picture of that right now. But it's by no means unique. So we need international management of the front and back end of the fuel cycle, uranium enrichment, plutonium disposition. We can produce that, but we're going to have, among other things, talking about U.S. leadership, U.S. participation with its own facilities. Not to say it's only those other countries who have to be shape up. We can internationalize our enrichment facilities, for example. So we have this various renewables options as well, and PV showing up in the form of rooftop, remote, and large field. We have concentrating solar power, which has this extra virtue that we heard about, that it's relatively easy to add some storage in the form of high temperature salts for at least extending the power about a couple of hours anyway beyond when the sun is shining. So there's going to be a rivalry between concentrating solar and PV for large facilities. I don't think concentrating solar goes on roofs. But it does compete at the big scale. And then we have wind, all of them intermittent. Many things to say about them, but I know I'm running low on time, so I want to just bring up the subject of the intermittency of renewables and penetration. I've been spending time learning about that. It's a bit of a shock to realize how much the experts have known all along that storage for multiple hours of electricity is pretty expensive, and that it is not the solution of choice for now. Load management, smart grids are better at this. And smart grids are very interesting because you start to say, well, when the wind is blowing hard, I will wash my dishes or clothes with a timer, I don't care. And that is pretty, you wonder why it's taken us so long to get there. It means spot pricing in the individual homes. Some of you know more about this than I, but spot pricing has moved down in size so that I know Princeton became a university's plant, became subject to spot pricing about 20 years ago. Presumably things a little smaller, like how shopping centers are getting that way now, but it's only a matter of time before everybody faces spot pricing, and then we have the smart grid. And that would make, it'll all work. There'll be intermediaries. You and I won't have to think about the details at all. We'll hire somebody to put something in our house to get the job done, share the savings with a person, and we'll have a smart grid. That pays a lot of dividends. But finally, natural gas is available as a partner to intermittent renewables. And the reason we don't hear very much about that, I think, is ideological. The renewables community can't stand the idea that there'll be a single carbon atom emitted when the day is done, even in an interim period. If it isn't 100% renewables, get off the reservation. Natural gas and renewables and many other combinations of fossil and renewables make lots of sense. If we get past the ideology and also have the idea that half a loaf is better than none, and realize that a system which is half natural gas and half solar is 4 times less carbon intensive than a coal power system. Relax and enjoy it, we'd be much further along. We can't do that in the current political framing of this problem where 90%, 95% renewables or low carbon is the only thing we're willing to settle for. I'm a slice and dice guy. And then I want to emphasize in my final slides that the way to think about solutions is to realize every one of them can be done badly or well. Conservation can certainly bring on more regimentation than you and I would like to see. Or even like to see if we concede that climate change is extremely important. Renewables bring on issues about competing uses of land. Clean coal, which is carbon capture and storage, has not just clean, it has to be clean upstream too, so it means we don't put miners' lives at stake, and we don't put acid into rivers, and we do it right, we don't take mountaintops off. Nuclear power has this coupling to nuclear war I've already discussed, and I'm not including in this talk, but some of people in this room know a lot about it. Paul is on a committee that is going to issue a report on this subject in just a couple of months, which is geoengineering, looming on. The more one says climate change is the only important problem in the world and we've got to solve it no matter what, and everything else will have to take a back seat, the more you take away the capacity to evaluate geoengineering critically. So in my view, the problem, it's a two-sided reasoning must be introduced. It's hardly there in the climate change problem. We must take into account both the risks of disruption from climate change and the risks of disruption from mitigation. We must not privilege the atmosphere. There's extra carbon because we dug it out. If we don't put it in the atmosphere, we get 350 parts per million, let's say. That carbon is in the land somewhere, unless we've stuck it deep underground again. So climate change is just one aspect of fitting on the earth. And so I recommend Hippocrates. I will apply for the benefit of the sick all measures that are required, avoiding those twin traps of overtreatment and therapeutic nihilism. Bob, is my time up? I could have a few end slides. Should I run through them? Okay, so science has introduced a big counterintuitive idea that human beings are capable of changing the planet at global scale. Forests have been cleared, fisheries have been depleted, low-cost oil has been found, the surface oceans are more acidic, and climate change is one more example of human beings changing the planet at planetary scale, which is an unwelcome idea. We wish we lived on a larger planet like Jupiter. Our problem is fitting on the Earth. And it's not surprising, given that this is an unwelcome idea, that there is a lot of pushback. Tell me it's not true. Take me to the bottom left of the top right corner. Galileo argued that the Earth wasn't at the center of the universe. That wasn't a welcome idea. He was excommunicated. Darwin argued that human beings were part of the animal kingdom. He had a mixed reception, but he was called the ape man in the popular press. The idea that humans can't change our planet is as out of date and wrong as the Earth-centered universe, but expect a lot of resistance. It took decades. We're not completely convinced in this country that evolution is right. I think we aren't challenging Galileo for the most part, and probably 300 years from now we won't be challenging Darwin either. In the past 50 years, we've become aware of the history of our universe, our Earth, and life. It's amazing to me when I think back about my career, how many of the big ideas that have past time in them, the Big Bang, formation of the Earth, continent separation through the rifts and plate tectonics, the DNA molecule, and so much more, have been found out in the last 50 years. But we have no systematic way of thinking about the future. And maybe it shouldn't be surprising, since it's only so recently that we've had any systematic way of thinking about the past. But someday, soon I think, there will be a Department of Destiny Studies at Rutgers, and there will be systematic thinking about 50 years versus 500 versus 5,000. The way we deal with waste disposal and nuclear power today indicates we don't know what we're doing with this concept. And we begin to ask what we are on Earth to do. 2 slides more. The world has why am I nonetheless optimistic? And Bresh had an interesting theme that we aren't too worried about the uncertainties in the world. Why aren't scientists more depressed when they know that important problems aren't understood? Well, it's because of a sense that there is an evolving story. The world today has a terribly inefficient energy system, so it can become more efficient. These are actually incandescent bulbs up there. Usually I look up these days and they're not. Carbon emissions have just begun to be priced. Most of the physical plant of the world is still being built, but an awful lot has been built since I started talking about this subject badly. cities all over the world being put with houses, apartment buildings, 10-story apartment buildings being built to accommodate tens of millions of people and built very, very cheaply with very cheap appliances in them with no life cycle maximization underway. And very smart scientists and engineers now find energy problems exciting. At some level, that's the real reason to be optimistic. And that wasn't true a decade ago. These energy centers at universities are not 25 years old. They're younger than that. There was a wave in the 70s, and that was what I was caught up in, and John Holdren was caught up in, and others. But this wave is not that old, and it's bringing in lots of smart people who say, this is what I want to work on. All in all, our science has discovered threats fairly early. One can imagine that we didn't have satellites to look down on the planet and to figure out about how the Earth worked. We didn't have ocean probes. We didn't have the modeling and the quantum mechanics to figure out about absorption by the carbon dioxide molecule. We have it. We can identify a myriad of helpful technologies, as I've been reviewing. We have a moral compass that tells us to care, not only about those alive today, but about the collective future of our species. We might not have that either. We need all three in order to feel that we're fortunate. What has seemed too hard becomes what simply must be done. Thank you.
Thank you, Rob. We're going to transition into a panel, but if there's a couple questions for Rob specifically, we can take that now. Yeah.
You wait for Mike.
Thanks for a wonderful talk. You link nuclear power with nuclear weapons. That's really not the case for thorium, and my understanding is that thorium is also generally cleaner.
I don't think so.
About the generally cleaner part?
I don't think it is. I mean, I think the issue is always, if you have a nuclear power system and you're a mischievous person, what would you do with it? And I've not learned that you can't get into lots of trouble. Thorium turns into U-233, which is a fissile material, and you can make a bomb out of it. So I think you'd have to be extremely. If you run any system properly with controls, you won't get into trouble. But if you start being able to divert materials, put them in surreptitiously and pull them out again, I'm not convinced that thorium is any better. I haven't worked on it as much as some people. I've never seen a simple, straightforward case. I've never seen the right question asked, which is, if you're mischievous, what could you do? Partly because things like that are not the things you want to write up too much.
One more question.
Who's the one more question? That young lady. Okay.
Hi there. First about that physics thing. When an irresistible force meets an immovable object, I saw this great cartoon that demonstrated that the force will just sail right through.
The force will sail?
Right through the immovable object.
Okay.
Okay. But the two things that I really, I'm definitely on the left side of the column, very optimistic. To me, once everybody sees it the way I do, we won't have a problem. And the things that work for me are the lifestyle change and the nuclear. And I just want to put out some references. First
You're saying you're here.
Well, yeah, either bottom or top. No, yes, it doesn't matter. I'm on the left.
Wait, oh, even here.
Yeah.
I didn't ask anybody about in that quadrant.
I apologize.
Yeah, so I have, I really see the world in I think different ways. I'm Iranian American, so the nuclear thing doesn't scare me as much as other people. I want a nuclear Iran. But the lifestyle change, the first most important one, just put out there. Jaron Lanier wrote this book, Who Owns the Future? And it's not about energy, it's about the network, but it fundamentally changes the whole equation. I want to just say, if you want some optimism, read that. And then, like I put out there, we should watch Pandora's Promise and look at nuclear energy. But the proliferation issue in particular, there's this gentleman named John Mueller. He wrote a book, Atomic Obsession, which does look specifically.
What's the name of the book?
Atomic Obsession.
Atomic Obsession.
Yes, and it really challenges the proliferation question. I would love to see that validated or invalidated in a discussion because it's very compelling.
Don't know the book. Send me a reference to it. I'd like to read it.